get started. Hello, everyone. Good afternoon or morning, depending on where you're joining in from. Welcome and thank you so much for joining us today. My name is Alex Burdett, and I'm here on behalf of the Agricultural Genomics Action Center, or AgAct for short. Uh, we're really pleased to be hosting this session and to have you with us. For those who may be new to our organization, AgAct is an innovative knowledge mobilization hub supporting Genome Canada's climate-smart agriculture and food systems research portfolio. Uh, a key part of AgAct's work is strengthening knowledge translation and ensuring research leads to meaningful outcomes for producers, communities, and the broader economy. Today's training opportunity is brought to you both by AgAct and Genome Canada as part of our commitment to building capacity and supporting knowledge sharing across the agri-food system. Before we begin, just a few housekeeping items. Please feel free to share your questions in the chat throughout the session. We'll be monitoring them as they come in, and we'll have time for Q&A at the end of the session. And if you'd like to have closed captions show up on your screen in either French or English, you can turn those on within the Zoom settings at the bottom of your screen. And lastly, today's session will be recorded and posted on AgAc's YouTube channel within the next week or so. And we'll be sharing the video and recording with everyone who's registered today. Okay, now on to today's topic. Understanding environmental impacts is becoming increasingly important across the agri-food sector, whether you're evaluating a research project, developing a new technology, or informing sustainability strategies. One of the most widely used tools for this purpose is life cycle assessment, or LCA. Today's webinar is designed to build a shared baseline understanding of LCA fundamentals. And we are delighted to have Fabien Hammerer here from 5R Enabler Designs and Operations, Inc., or 5Redo, facilitating today's session. 5Redo is a circular economy innovation and consulting firm specializing in the development of practical solutions and technical support to improve environmental sustainability. The organization works with businesses, researchers, and partners across the sector to integrate sustainability practices into products, processes, and decision-making. Fabien is the Chief Technology Officer at 5Redo and leads the company's lifecycle assessment and circular economy integration activities. Over the course of his career, he has conducted and directed numerous LCA studies across a range of sectors, including manufacturing, packaging, polymers and biopolymers, and food and beverages. Prior to joining 5Redo, Fabien earned his PhD in chemistry from the Université Paris-Sud and completed his postdoctoral research at McGill University, where he developed enzyme-based technologies to reduce water use. His work has since focused on advancing sustainability through green chemistry, circular economy approaches, and environmental assessment. Fabien is a recognized public speaker and educator who regularly engages audiences across Canada and internationally on topics related to sustainability, circular economy, and environmental innovation. We're really excited to have him here to learn from his experience. And with that, I will turn it over to Fabien to get us started.
Awesome. Thank you, Alex, for the kind introduction. And hi, everyone. Very pleased to have been invited by AGACT, to to present today and introduce LCA. So I will assume everybody is seeing the presentation right now. So today's presentation is called Introduction to Lifecycle Assessment. You can consider it like an extremely fast LCA 101. And for that, I'm just going to dive right in and talk about the philosophy behind lifecycle assessment, which is lifecycle thinking, which basically stems from the observation that the life of a product or a service doesn't start at the manufacturing site and it does not end when it's thrown out. So basically, if you want to evaluate the impacts of that product or service on the environment, if you want to quantify this impact or compare two products, one needs to take all the phases into account, from material extraction, how they're being transported, processed, the product is manufactured, how it's distributed, how it's being used, and finally, how the materials are handled at its end of life. So this is the requisite for this for this presentation. But what I'm going to focus on here is the process of conducting a life assessment. This is presentation is based on the ISO 1440 and ISO 1444, which basically spell the rules for the terms to be used when conducting a life assessment, and also how to proceed with the study and how to report it. So a typical life cycle assessment goes into four steps. The first step is defining the scope and objectives. So you want to make sure that you know where you're heading. Then you go into the life cycle inventory, and we'll go over each step individually as well, followed by the life cycle impact assessment. And this one might be the most obscure at this point if you're not familiar with life cycle assessment, but we'll break it down later. And finally, life cycle interpretation, which ties the whole lot together. So moving to the first section, scope, this is the one that basically tells you, or like helps you move from why you want to conduct an LCA to how to do it and how to set the term to meet your objectives. So each element of a goal and scope of an LCA, basically I found answers a typical question. So the first thing you want to do when conducting an LCA is make sure that you have clear objectives. So you want to figure out the reasons why you want to conduct that LCA. And that is paramount to know how to do so, right? So the next objective is the next part of the goal and scope definition is the function or functional unit. Is what are we looking at? What does the product achieve? And then how much of it do we base the study on? And the functional unit is basically the normalized quantity to which all the flows in the LCA study are going to be scaled to. You want to define your system boundaries, which basically is deciding which flows or like which part of a life cycle assessment and which processes are included or excluded. So it's basically asking the question, what matters in terms of the part of the system that we want to study to meet our objectives. You also want to set data quality requirements. So when it comes to data, you want to ask yourself the question, what's good enough? What do I need to know and to which extent to meet my objectives? And finally, cutoffs. We'll see later that they're conducting a fully comprehensive LCA and fully accurate LCA is basically impossible to conduct because we're working with extremely complex systems. So to take it easier on you, setting cutoffs or deciding, okay, what's enough to get to meet my objectives in terms of completeness or accuracy, like can help you make that study manageable. So once you have set all these terms, you can move into what is the core of life cycle assessment, which is to create the life cycle inventory. Or like it's something that will help you reveal the hidden activities behind the product or service you're studying. How does that work? So if you look at any product, and in that case, I chose this wonderful tractor. Um, Well, we all know that, or like we all conceive that there's a lot of activities coming into manufacturing that tractor, from resource extraction. That those can be organic, bio-based. They can be fossil. They can be mineral, and all these materials need to be processed, assembled, need to be manufactured into the final product. And this product also needs to be distributed, warehoused until it can be put to use. And all of these steps require themselves, like at the very minimum, some energy to conduct, some water, and countless other products like detergents for cleaning, like additional fuels, like metals, it generates waste, etc., etc. All of these need to be taken into account when you conduct a life cycle assessment by definition. And at the end of the life of that tractor, what you're going to get is for it to be transported to whichever plant or facility in which it's going to be dismantled, deconstructed. Some of that waste, or like some of these flows, may go to landfill. Some of those may be incinerated to recover some energy, or just incinerated downright. And finally, some of those some of those materials may be recycled and put back into the industry, or like into upstream parts of the process, whether it's related to manufacturing the new tractor or other product. So as you can see, there's a lot of things, a lot of materials, and lots of considerations that go into the life cycle of any product. And the life cycle inventory is making a list of those so that we know exactly where these flows interact. I'm sorry, phone ringing. My apologies. So that we know exactly how these flows interact with the environment. What the life cycle assessment does is that on top of the standard phases of the life cycle of the product, it brings to the surface what we call the background system. So how these um, phases that are targeted on the product are actually fed by another system that is deeper, called that we can call the supply of supplies. So how things are made so that they feed into the life cycle of the product, and how each of these phases also generate waste into what is called a discharge management. And the life cycle inventory also can look and take into account how the supply of supplies management and discharge management background system elements interact as well. And what life cycle assessment truly relies on is how all of these taking place within system boundaries that were defined at the scope level interact with the environment. So basically, what we want to know and what quantify by doing the life cycle inventory down the line are all the inflows coming from the environment into the system boundaries, whether we're talking materials, energy, and these inflows can come from raw material extraction, from resources all around, whether they're renewable or not, and also looking to quantify the outflows, like regardless of their nature, they can be gas, solid, liquid, energy, and regardless of where they're emitted into any kind of compartment, like the soil, rivers, ocean, etc., etc. The life cycle inventory is the core of life cycle assessment, and this is what allows us to quantify the impacts. Here's an example of what a list of inflows at the exchange level in the lifecycle inventory looks like. So this is just an extract of a few entries from inventories that can actually inventory or like list hundreds to thousands of substances. So the first one is like aluminum taken from the ground, and the amount reported here corresponds to the aluminum amount taken from the ground and required to deliver the functional unit, which in that case is to the making of a tractor. And we can do the same for antimony, argon, arsenic, etc., etc. And you'll see here that I put those for CO2 taken from the air, CO2 that is non-fossil, and also carbon that is like organic carbon that is taken from the soil, organic carbon that is actually put back into the soil. And you can do the same thing for the outflows, as I mentioned. So again, you'll have thousands of substances that can be emitted from any point in the life cycle assessment. So you'll have these very fancy chemical names like the 1112 tetrafluoroethane, etc. And the inventory specifies whether it's emitted to air, water, rivers, soil, agricultural soil. And again, you get an amount corresponding to the amount of that substance that is exchanged for a given functional unit. Well, now you might ask, me or yourself, pardon, ask me or yourself, like, okay, but how do we get there? Like, do I need to measure all of these myself? Like, how does that work? Well, to build the inventory, we typically rely on two types, or like three types of data. Sorry. The first one is called primary data. This is what is directly measured for the purpose of the study. So if you're looking at a given tractor, you want to know exactly which components it's made of. You want to know how long it's being in use, what are its repair, maintenance, conditions, etc. But that is not enough in itself to create the inventory that we've talked about, right? Just knowing what you can measure directly as a tractor manufacturer is not enough to go there, unless you're willing to spend infinite amount of resources on this. So the second source of data that we can use is called representative data or secondary representative data, which is already existing and data that is compatible with the objectives of the study. That means that it's data that will satisfy your data requirements. This is the data that we typically take from LCA databases, and I'll come back to those later. The advantage of that is that you can use that data to fill up the gaps that you cannot yourself collect with primary data. This data includes industry averages across geographies, across domains, services, products, etc. If we come to actually knowing like what the balance can be between the two, there's two major considerations. Primary data, because it's measured, can be directly considered as accurate, but this comes at the cost of a lot of effort to collect. You need to get the organization, or like to know, to or like the organization to organize to collect that data if you're working with someone. On the other hand, representative data is directly available, but as it relies on industry averages or specific measurements, this is less accurate because less likely to be perfectly fitting what you're trying to measure. So there's directly a trade-off between primary and representative data, and the balance you must strike depends directly on the resources you're ready to spend on your LCA. And finally, I'm going to talk about proxy data, which is not entirely representative placeholders used in the absence of either representative data or primary data. So they're kind of like gap fillers. They're basically assumptions that you can approximate, that allows you to approximate the actual lifecycle inventory and down the line your own impacts. They're less considered, in general, less accurate than representative data, so their use should be avoided if possible. So talking a little bit about secondary data and LCA databases, they have the immense convenience that they present aggregated data. What I mean by that is that the background system is included in the process description that you will select or take from that database. So if you look at a given process, that could be, for example, making the wheel of the tractor. When you select that tractor wheel entry in the database, the impact like already include everything that comes upstream from this. That means that you don't have to go and like look yourself for what does the tractor wheel making industry look like to use it. Is just you just use it like this. And that is a huge game changer when it comes to LCA, that these databases exist and have gone through the effort of aggregating the upstream data leading to a given product or element of a system. Examples of databases, like probably the two most known and widespread databases and generic databases are EcoInvent and Sphera. EcoInvent is a nonprofit situated in Switzerland. Sphera is a for-profit located in Germany. So Europe leading the way. Because I assume here I'm going to have a more agri-ag-tech oriented, an agriculture oriented audience, agriculture is very well covered compared to other sectors, with additional databases like agri-footprint, the World Food LCA database, and in a more European slash French lens, AgriBalise is also very detailed, although its geographical relevance is somewhat limited for North America. Other advantages of LCA databases is that they're updated and expanded regularly. There's been huge progress when it comes to the coverage that they have and the accuracy that they reach. What they give you is industrial averages across various geographies. So you will find, for example, the wheel tractor making in in Europe, in Switzerland, in North America. The coverage is not perfect when it comes to geographies, so you sometimes have to consider adapting one entry from one geography to the other. But again, because they're industrial average, they introduce inaccuracy or imprecision in your LCA because they might not relate exactly to the product system that you're studying. So they are convenient to use, but again, primary data, if you can access that, is the gold standard for your LCA. And now talking about proxy data, as I said, proxy data, they're basically assumption or a hypothesis, but down the line is data that is not entirely representative or for which you know for certain that it deviates from what your from the actual system. So when using proxy data, there's two things you should keep in mind at all times. First is the conservativeness principle, which extends to all environmental reporting, that data gaps should not lead to exaggerated positive claims or what we call greenwashing. And if you're conducting a comparative study, then the assumptions should always favor the baseline so that you don't exaggerate your claims. And the various sources that you can find proxy data sources include peer-reviewed publications. Like there's a lot out there, but they not necessarily have made their way into the databases, so they're considered proxy data. Other LCA studies, if their methodology is similar, and you can also rely on statistics for the use phase. Typically, how well is your tractor? How long is the tractor being used? Or how often? How well is it maintained? Like how do repairs happen? Like these can be taken into account. That can also include national recycling rates for given materials. The point here of that slide is that to remind you that you should always or that proxy data before you should always be subject to consistency and plausibility checks. You should never use it for granted. One example that happened to me personally is using a peer-reviewed publication, ended up grossly overestimating the water use of the client organization I was working with. And by grossly, I mean we ended up with a water footprint that was thousands of times that of the comparison baseline, which did not make sense. And it turns out that the peer reviewed, that the publication had that like 10 to the power 3 error in the water it reported, and that shed doubt on the whole publication as well, on the whole document. But the idea is that whenever you input numbers in your model, consistency and plausibility should always be in mind. So now, how do we go from that huge list of chemicals and exchanges between the technosphere, the human activities, and the environment? This phase is called the Life Cycle Impact Assessment, or LCIA. I like to basically present it as three magic tricks, Although, like, if we're talking about magic, I'm a terribly bad magician because everything is transparent and I'm going to tell you all the tricks. So basically, LCIA helps you bridge the gap between the actual human activities and quantified impact. And we've seen that the first step to bridge that gap is a life cycle inventory. And the idea now is like what comes in between, and also how do we actually consider, like, what do we consider impacts? How do we report those? And there's several ways to do that. But the answer here, that the base principle is what we want to do is understand the causality chain of exchanges between the technosphere, so human activities, and the environment. So what we do is start from our life cycle inventory with that huge list of substances that we know are being exchanged between the environment and human activities. And the first trick of LCA is to convert these exchanges into direct impacts. What do I mean by that? Well, if we take the first substance in this list here, CO2, we know that CO2 causes climate change. It's a greenhouse gas. It will absorb infrared light from the sun, heat up the atmosphere. We know methane does the same. We know CFCs do the same. And by CFCs, that's the carbofluorocarbons, that chlorofluorocarbons, my bad, sorry, which not only cause climate change, but also ozone depletion. Phosphate and nitrate cause terrestrial acidification and eutrophication. Chromium causes cancer toxicity, and uranium causes ionizing radiation. So each of these substances, when they're released into the environment, will have a direct impact. And each of them, each of those impacts is of a different nature, which can all be quantified by measuring those impacts. So we know that methane over 100 years is 80 times more potent than CO2, if I'm not mistaken. Don't take that number at face value. But we can quantify climate change using the unit called kilogram CO2 equivalents. This is probably one that you've run into. We can do the same thing with ozone depletion by selecting a specific CFC, in that case, that's CFC 11, and normalize all the ozone depleting substances according to that unit, so we can aggregate the impacts of all ozone depleting substances. And we can do that for all these direct impacts, which are called midpoint indicators of impact. So yeah, that's great. Let's see what it looks like. All right. You can look there. The problem with this approach, direct approach, is that there are so many direct impacts that these substances can have. So we've talked about global warming, eutrophication, acidification, but we can look at ecotoxicity in freshwater, terrestrial systems, marine ecosystem, etc. So if you're a company executive in charge of, in this case, comparing product A and product B, can you use that graph to make an easy call? Is it something that, like, seems like an easy decision for you, knowing that you're going to engage your organization in one way or the other? Like, you could say in that case that it looks like product B on average, like, actually comes out on top in more categories, right? So it could look like product B is worse than product A. However, you can see a few categories in which product A leads to more impact than B. And in that case, how do you relate and how do you compare stratospheric ozone depletion to global warming? Is there a way to compare those? That's where the second trick comes in, which is converting those direct impacts to damages. Coming back to the list of impacts now, each with their own units, we can explore the causality chain further by thinking about what these impacts cause in terms of damages. We know that climate change basically leads to the extinction of species or the loss of biodiversity. ozone depletion will contribute to that, terrestrial acidification, etc., etc., each to their own um, extent. And the extinction of species, the loss of biodiversity, can be um, normalized in a single unit called species year. We know that climate change and all these direct impacts are also going to cause impact to human health, which is basically loss of life expectancy from humans. And this is expressed in DALY, disease adjusted life year. And finally, as well, using resources that are non-renewable now makes them unavailable in the future. So we're basically damaging the capacity of future generations to use the resources that have been used in the past. And these ones in a bit more of a like underwhelming consideration are expressed in dollars, US 2016 dollars, if I'm not mistaken. So basically, you've aggregated very different impacts into three damage areas. And now, like each of them participating to different extents to those, these are called the endpoint indicators. This means now, as a decision maker in an organization, from 40 odds categories, you only have three. You can look at the damages to ecosystems, to human health and resource depletion. And it looks that in that case, product A is is um, is basically performing better. Note that the two examples that I gave between the previous one and this one are not the same. So they were not talking about the same product A and B than in the previous example. However, my point here is that it's much easier for a company to make a decision or for someone to make a decision based on three indicators rather than 40. So now, like, can we actually go further? Like, should we actually go? Well, the third trick is basically aggregating damages to a single core that we could call overall impacts or overall damages, which is measured in person year equivalents. So this is a technique that is possible and practiced, but there are major caveats to it. The first one being that it has an inherent subjective component. While the first two steps were purely quantitative and can be based on facts, this one has a level of like value calls. There's no objective way to value the extinction of a species with the loss of life from the human population or to the non-renewable resources depletion. This has to be something that is arbitrarily decided and that has to be based on the values that one holds. So it means that we step away from objective quantification to just making a call. And also the unit here, the person year equivalent, which is corresponds to the use or the amount of damages a person would make over the year in terms of an average on the planet, makes little sense given the high diversity of impacts generated by people depending on where they live. So this is something that can be done, and this is called the weighed score. This step is called weighing, and it is practical from a decision-making point of view because then you can have product A versus product B. That's okay. Product B is more efficient or less impactful. Let's select this one. We move on. This is great, but there are trade-offs, which I'm going to go through just now. You have to keep in mind that all three levels are as useful, but they will depend highly on which objectives you set for your LCA. Midpoint indicators, we've seen they're great to give you a comprehensive overview of the environmental effects of a product and to compare those across many categories. They allow you to identify internal trade-offs. So the trade-offs is where we saw that inversion between product A and B across different impacts. And they also have a higher accuracy because they rely on less um, mathematical modeling. Their weaknesses is that they require some environmental knowledge to make sense of those. It's not everybody that is necessarily familiar with eutrophication or acidification or various other environmental or human toxicity impacts. They're harder to draw general conclusions from, as we've seen many indicators, and that can be disorienting to decision makers. Normalized endpoints, they provide an aggregated overview into intuitive areas of protection. It makes more sense to people to know that we're doing damages to ourselves in terms of toxicity, damages to the ecosystems, and damages to by depleting non-renewable stocks. They're therefore more action-oriented with just three indicators to weigh, and they still allow partial trade-off identification, meaning that you can see if a product like may be better for the environment, but down the line worse for human health. In terms of weaknesses, that's one of their weaknesses exactly, that the trade-off identification is partial. You don't know in which compartment of these um, impact areas you're actually affecting. You have a higher uncertainty because further aggregation, so further mathematical modeling and approximation, and you do not, you cannot compare between areas of protection. And that's where finally the weighted endpoint score comes in. It's a single score output, offers comprehensive comparison between options. It's very intuitive and action oriented. But as its weaknesses, as I already mentioned, it's based on a value judgment. It's blind to internal impact shifts, and it offers like higher, or like the highest uncertainty of all three. The choice of where to go and where to start in terms of that process really depends on the objectives that you set out for yourself. If your goal is to quantify only greenhouse gases emissions, then the midpoint indicators is enough for you. If you want to have a more comprehensive view um, about the actual like holistic perspective of the impacts you're generating, then the normalized endpoint or weight endpoint might be better for you. And if you have no time and just need to make the executive decision, maybe the weight endpoint like works for you as well. So now talking about LCIA methods. So the tools that allow us to convert the lifecycle inventory and the substance being exchanged to direct impacts, to endpoints and damages, to the final score. They're basically mathematical models that convert one from the other. So we have typically two types. There's the generic ones that will cover most of the like most, if not like many impact factors. For example, recipe 2016 is is used in Europe. Impact Work Plus, probably a bit more America. And we also have the EN 15804 plus A2, which is also called Environmental Footprint 3.1. This one is dedicated to environmental product declarations, which I'll come back to later. So these are the methods that typically allow that three-step approach. But you can also find some that are problem-oriented, with also like probably the most famous one, which is the IPCC 2021, which is for greenhouse gases emissions. You'll also find others on water scarcity, land use, etc. And it's often that the generic methods pull from problem-oriented emissions to get their direct impact and midpoint indicators. So things to keep in mind about LCIA is that the outcome of an LCA and of the LCIA phases hinges on many methodological choices. They will depend, of course, on the functional unit that you're choosing, the system boundaries that you're adopted, the data quality requirements that you set for yourself, And finally, the nature of the LCIM method. That's only for the main ones because every single decision that you make is going to have an influence on your results. And that makes it difficult and borderline impossible to compare independent studies, unless you're extremely careful and lucky. That may happen. So, the solution, if you have to adapt findings from like a previous study, is to go back to the life cycle inventory that is hopefully shared with that study. That will be the case typically in that would be the case typically for peer-reviewed publications, and not always if you're working from LCAs that are published from by companies or shared by companies. Going back to the life cycle assessment, life cycle inventory allows you to recreate the outcome of a study based on your own chosen methodological choices. So what it does is that it will adapt that inventory to your own choices, to your own goal and objectives. Now, what to make of all this? We're going to the last step of the process, which is the life cycle interpretation. And to me, that is the real value of LCA for decision making, for reporting, etc. The first thing that it's supposed to do is to basically reveal the full meaning of the impact assessment and of the results. And the LCA results, as I just mentioned, are inherently highly context dependent. They will depend on the initial objectives you set yourself, system boundaries, data used, assumptions, cutoffs, etc. So the role of the interpretation is to tie all of the elements of this original scope to the results and explain how they relate to each other. And the second side, like the second side of the value provided by that section, is the usable insights. That section highlights how the study informs decision making. So it's supposed to comment on the robustness of the finding, on the limitations of those findings, provide conclusions, and not mandatory recommendations to lesser or to reduce impacts in the future. So, reporting in LCA, as I mentioned at the beginning of the presentation, is governed by ISO 1444, which is called Lifecycle Assessment Requirements and Guidelines. It contains very specific practices regarding the conduction of the study and the requirements on the report content based on its objectives. Especially, it will mandate an independent external review in case of public disclosure of an LCA, but only for comparative studies, meaning that it's only studies that compare product A and B and actually try to influence the public regarding the life cycle impacts of these two products. These are considered higher stakes and need to be externally verified. In the case of the academic publication, the peer review plays the role of that external review. So this is it for the LCA, like the conduction of an LCA. I'm just going to make a few quick mentions for other LCA-based techniques and services that you might have encountered and might have some questions about. So the first one is one that I mentioned, and it's called Environmental Product Declarations, or EPDs. This, the EPD methodology is basically a tentative harmonization of the LCA methodology at large. So basically, it's trying to make methodological choices for the LCA conductors so that independent studies get more comparable. This is a self-declaration at product level. So it's basically a manufacturer of a product or deliverer or a service that can choose to conduct or to release an EPD, or it can be mandated by regulation like it is in Europe. EPDs is originally a European initiative. Typically, what is required is the reporting at midpoint level, so direct impacts using a dedicated LCIA method. So that's the EN 15804 plus A2 that I mentioned earlier. And these, before publication, are externally reviewed to make sure that the study being published satisfies the LCA methodology aspects that were set by the program. These are ruled by ISO 1425, which is itself based on ISO 1440 and 1444. So um, the two frameworks are compatible. Just know that like what it does is provide a strong framing for comparison of two products delivering a similar function or the same function. But because several programs exist and have been implemented, comparability is reduced from one program to the other because they did not adopt exactly the same methodology. So this is something that a new European framework is trying to address. It's called the environmental footprint, but it's not taken a real hold it's just being rolled out in Europe and hasn't taken hold in North America. So we're still waiting to see what it's going to look like. Another example of derivation of life cycle assessment is also the life cycle costing, which is life cycle thinking but applied to monetary aspects of a product use and typically ownership. So just like we said at the very start, the total cost, like for a product and environmental impacts, the total cost of ownership is not limited to purchase cost or just the disposal cost either, but you have cost all along the way. So for now, LifeCC is quite limited in its use to long-lived assets, so typically the built environment, and that's the only sector for which an ISO standard has been released. This is directly compatible with LCA methodology, and LCCs are actually directly integrated in major software. And I believe that EcoInvent is also partially covering LCC by providing value for some of the products and processes in the database. And the corresponding ISO, if you're curious, is 15686-5. Another derivation from life cycle assessment is the social life cycle assessment, SLCA. And that stems from the observation that the environment and health are not the only systems affected by human activities, but it's not only like what we do, it's also how we do things and how our workers and communities and stakeholders across the board being affected by human activities. So the process is similar to a classical LCA, where you'll go through all the processes within system boundaries and try to evaluate the impacts of each of these. In that case, the impacts, social impacts, are typically risk assessment evaluations. They're often tier-based of the harmful practices to workers, local communities, consumers, children, and like overall value chain. In one of the methods, there's up to 34 indicators or more like risk areas. Aggregation methodologies exist, but are limited by intrinsic subjective considerations. It's hard to see how consumers being affected relates to children being affected or local communities and risk to workers. And finally, the main databases, if you're curious about this, are SHTB, PSI, LCA, and UNEP, which provide each some data for global supply chains. Just want to mention that while in LCA databases are separated from LCIA methods, in that case, each of these databases, as I understand it, have their own rating system and risk assessment systems. So there's a bit more of a siloed approach at the moment in social lifecycle LCA. Hopefully that will be sorted soon for better coverage. If you're curious, ISO 14075 is your go-to. And finally, carbon footprint. So this one is back to environmental environmental impacts, but with a focus on climate change as a single issue. You will you will apply exactly the same methodology as for LCA, the same approach with the 4 steps that I mentioned, from scope definition to lifecycle inventory to LCIA and interpretation. But you will focus on a single impact factor category, global warming potential. LCA breaks down in that case the method, like breaks down that single issue into different type of carbon emissions and removal. You will look at fossil and biogenic carbon, aircraft, what like GHG emissions linked to aircraft, direct land use. So the way we manage land in that case is taking like a huge part in what we do, and land use itself is also included but non-mandatory. So direct land use change means like how much of forest gets deforested into agricultural land, or agricultural land turned into parking lots, or well, that's just an example, but you see where I'm heading, I hope. So there's typically a bit more data available for carbon footprint, and it's also more affordable than comprehensive LCA databases because they focus on that single issue. And for that, the ISO you want to turn to is 14067, which also relies heavily on ISO 1440 and 1444. And sorry, I used the wrong finally, but you might have come across this tool called Holos, which is a Canadian like specific tool for GHG quantification for farms in Canada at the field or organization level. It's extremely practical because it's a fully integrated tool to determine GHG emissions of farms, like from the field scale, and aggregate it, if necessary, to the farm scale for cultivation or grazing. So anything linked to agriculture. It is very detailed, like in terms of geography, culture, practices. This is a really advanced software and very practical as well. And what you get out of it is the field to farm level emissions. But you never get to define a functional unit. This is an organization level tool, not purely one with LCA. And what you get is an inventory of GHG, but also not directly the reports. You have to, if you want to report according to any regulation, you have to do that yourself. So as I was reviewing it for this presentation, I could not find a direct alignment with ISO 1444, especially when it came to defining the scope. So the tool itself may enable lifecycle assessment that is compliant or aligned with ISO 1444, but the tool itself is not. If I could find one alignment that was more with ISO 1464-1, which is the GHG quantification at the organization level. But again, that is partial alignment, not compliance. So, conclusion here. The few takeaways that I want you to, well, take away. First is that LCA reveals the background system behind any human activity. All we do relies on infrastructure and supplies that are difficult to intuitively picture, and LCA brings that to the surface. LCA translates emissions into impact into damages. It draws on scientific knowledge in multiple fields to explore the causal relationships linked to the taking, like the extraction or emission of substances to and from the environment. The LCA approach allows for flexible reading frames. And that's, to me, one of its most important powers. It lets you choose your interpretation level based on your objective. Many methods are available. There's bound to be one for you. And finally, LCA removes environmental blind spots. It enables informed decision-making by identifying impact shifts and trade-offs in each impact area. And that will allow people and organization from focusing so much on an indicator that they'll forget the others and down the line cause more harm than good. And finally, what makes a good LCA report? Well, You will want to have clearly stated objectives and scope. As I said, they condition heavily the methodology of the study, and they shape the results. You want a comprehensive life cycle inventory. It should reveal as much of the background system as possible. If sometimes like you deal with confidentiality issues, then you want to at least have strong data quality requirements. You want results that respond to objectives. You want to make sure, that the results respond to the objectives, that they have an adequate level of impact assessment that match the scope. And finally, you want a comprehensive interpretation section. As I said, this is where the value lies. You want a strong contextualization of the findings so you know how to act, which is what life cycle assessment is trying to do. It's trying to shift things from harmful environmental practices to more respectful practices. Thank you for listening to me.